In order to explore some more about how primitive types work, we're going to play with generating random numbers. So our goal is to generate a random integer in a range.
That's like asking the computer to pick a random number between 1 and 10.
In the lab, we are simulating the roll of a die, but this technique could be used a bunch of ways. For shuffling cards, we'll do that soon. Picking people to survey, randomizing a playlist, there are many, many more. Making a random number is actually a big research topic because computers don't just make things up. Java gives us a start by giving us a pseudo-random number generator, math.random. Pseudo-random number generators feel like the numbers they give us are random, but they are really found algorithmically. If you're interested, Wikipedia has a good article explaining how these things work. For us, we're going to use this lab to prove that math.random does truly simulate a random number generator. Math.random is a good start, but it gives us a pseudo-random number that only contains the decimal part of a number. This means that it is less than 1 and positive. In other words, the value it gives will be between 0 and almost 1.
It can give 0 on the low end, but on the high end, it can get to 0.999999999999999, but it can't get all the way to 1.
In order to get a bigger range of numbers, we multiply the value math.random gives us by the number of values in our desired range. If we suppose we're simulating the roll of a die, we want to randomly generate an integer between 1 and 6. That is 6 possible values, so we multiply by 6.
If math.random gave us something close to 0, after multiplying, we'd still have something close to 0. But if math.random gave us something close to 1, after multiplying, we'd have a value close to 6.
At this point, the smallest number we can generate is 0. In order to shift the possibilities into a range that starts somewhere else, we add the bottom number of our desired range to the calculation. So simulating a die with a minimum value of 1 means that we would add 1.
Now, the range of real numbers that we would have would be between 1 and almost 7.
Finally, we typecast that value to an int. That will truncate it, giving us the integers between 1 and 6. Here's the code for those steps. First, let Java generate a random number between 0 and 1.
Remember, it can generate 0, but it can't generate the 1. It can just get close to it.
Then we multiply it by the number of values in our range. We add the minimum value of our range, and we typecast it to int. We could also choose to put all of those calculations into one statement. Let Java generate a random number between 0 and 1, multiply it by the number of values in our range, add the minimum value of our range, and typecast it to int. Let's look at some more examples to see how this works. In this first example, we're multiplying math.random by 8 and adding 13. That means we want to generate 8 values starting at 13. So our range will be from 13 to 20. In the second example, we're multiplying by 10 and adding 4. So we want our range to start at 4 and have 10 values. So it will be the values from 4 to 13.
Watch that last one. That typecast is being applied to the math.random before the multiplication. Think about what that does. It makes the math.random result get truncated to 0. All of the randomness is gone. Anytime your random number doesn't seem random, look for this kind of bug.
That's right, Zumi. When we truncate the math.random because it gets typecast to an int, that makes it be 0. 0 times 100 is 0. 0 plus 5 is 5. So we're not going to get a random number at all. We're just always going to get the integer 5. The code in the lab generates the random number in 2 steps. It does the calculation through adding the minimum value and stores that result into random real. Then it typecasts that result to get the random int we need. One source of bugs is that things behave a little differently when numbers are negative. So let's see what happens if our range includes both positive and negative numbers. If our minimum value was -4, and we wanted a range that has 6 numbers, the numbers we want are -4, -3, -2, -1, 0, and 1. In our calculations, we'd multiply by 6 and add -4 before we typecast to an int. If math.random returned almost 1, then random real would be almost 2. 1 times 6 plus -4 is 2. If math.random was 0, random real would be -4. That feels like the right range, from -4 to 2. However, when we typecast it to an int, we're going to have trouble. Remember that typecasting just throws away the stuff after the decimal point. When we do that to a positive number, we get an integer below our real number.
Think about what direction that goes on a number line.
However, think about what happens if we do that to -2.5. Truncating -2.5 will give us -2, not -3. That's moving in the opposite direction on the number line. Let's look carefully at what's happening here. Our goal is to end up with a random integer between -4 and 1, and for all of the values to be equally likely. Random real will contain a value somewhere between -4 and almost 2. When we truncate the values between 1 and almost 2, we'll get 1. And when we truncate the values between 0 and almost 1, we'll get 0. That's working just the way we expect. However, let's look at the other end of the range. If we generate -4 exactly, which is a possibility but not very likely, that would truncate to -4.
Now I'm worried, because you won't get as many -4s as the number of positive ones we got.
Me too, but let's keep going. Every value of random real between -3 and almost -4 will be truncated to -3.
That doesn't feel too bad. The numbers are going the opposite direction as they were when we were working with positive numbers. But we'd get the same number of -3s as the number of positive ones we got.
I agree, and that trend will continue for the rest of the negative numbers. Values between -2 and almost -3 will truncate to -2. Values between -1 and almost -2 will truncate to -1. And the last one of those is that the range from 0 to almost -1, all of those will get mapped to 0.
Wait, that's bad. Truncating everything from 0 to almost 1 already has given us zeros. Now we have twice as many zeros as we want.
Yep, there's the problem. Since the truncation is going in the opposite direction when we switch from positive to negative, twice as many things get mapped to 0. We won't get the number of -4s we want, and we'll get way too many zeros. That won't do. Java gives us another function that helps here, math.floor. It takes a real number and gives you back the largest integer below that number. Math.floor of 3.2 will give you 3, while math.floor of -3.2 will give you -4. Essentially, it's making sure we always go the same direction on the number line. Surprisingly, math.floor returns a double, even though it promises that there will be no fractional part.
I have no idea why they would do such a silly thing.
There are technical reasons why they do this, but they're a bit beyond us at this point. We just need to typecast the result to get the int that we want. So, in this video, we learned that we can use math.random to generate random numbers, and that there's a standard strategy for using that to generate integers in a given range. But there are complexities if that range includes negative numbers. In those situations, math.floor comes to the rescue.